Hey, hi guys. So welcome to my live stream. This is a bit new for me. So please give me some constructive feedback. Let me know, what am I doing well? What am I doing poorly? Do I need to be a little more lively? All right. Okay, great. I think it looks like we are back. All right, let's see what happens if I need to re-upload. We can do that. Or if I need to put in a little bit of a timestamp so you guys know where to jump forward to, I think that'll be fine. Okay, so let's try this out. All right, so hopefully you guys can see this. I'm going to be talking a little bit about binomial and geometric distributions. I've got some problems here. I'll be posting them to the Google Classroom if you want to work along with me. So yeah, let's go ahead and try this out. All right, so binomial and geometric distributions. So let's kind of remember, let's make another page here. All right, so remember binomial and geometric distributions. So what do these things talk about? Well, hopefully we remember from lesson, this is all in, right? Lesson 6.3 in the practice of statistics. So if we remember a binomial distribution, right, this tells us what's the probability of getting X successes out of N number of trials, right? So if I roll a die, 20 times, what's the probability that I roll 4 times? After that, right, we also had a special case of this called the geometric distribution, but I will get back to that in just a minute. All right, so let's go back. Okay, so if we're looking at this today, okay, so here is our problem that I kind of set up here, right? So this one's a little bit morbid. It might be a little bit dark, but again, we're in the middle of some dark times, so maybe it's a little appropriate, maybe it's not. Again, let me know in the comments what you think. So let's assume that the death rate for just a random person, right? We don't know anything about the person. Is this person young? Is this person old? Does this person have any health problems? We do not know, right? This is just a random person. So for any random person, right, we're assuming a death rate of about 5%, right? So if 5% of those who express the symptoms will pass due to them. All right, and so we've got some small local hospital, 50 people entered it yesterday with COVID-19 symptoms. So now the doctors, they're thinking about, well, what can we expect out of this? Okay, so let's start by looking at what's the probability that 1 out of those 50 will die. Okay, so we can do this 2 different ways, right? We can either do this by hand, or we can do this by calculator. So let's start with doing it by hand, and then we'll show the calculator as a bit of a kind of like an easier kind of trick for working with this, right? So this is a binomial situation, right? And we have to ask ourselves, how do we know that it's binomial? And we know that something is binomial because it follows the following conditions known as bins, right? Binary outcomes, independent trials, number of trials is fixed, And our last one, success chance is constant. Okay, so basically, remember, so right, do we have binary outcomes? Yes, we do. A person is either dead or not dead. That's it. There's nothing, kind of in between those two. Maybe if we wanted to get nitpicky, we could start filling out some details of this. We could say, well, okay, you could hypothetically imagine that like someone comes in with COVID symptoms and then dies from something completely different. We don't know. And so in that case, right, does that count as a death due to COVID? Does it not? We're not going to kind of get into that level of detail. We're sort of assuming that, like, if a person comes in with COVID-19 symptoms, we're only counting deaths that can be reasonably attributed to those. So we're going to assume that this is binary, right? Either dead or not dead. Independent trials, right? So we basically have to assume that this kind of goes with the idea of that the success chance is constant. Basically, we want to make sure that like each person we're looking at, that there's an independent, like their probability of death is independent of the other people we're looking at, which for a contagious disease may not be true. But for right now, we're going to assume it is, right? Let's assume that this is a reasonably well-equipped hospital. They're able to isolate the patients. And so, right, what's happening to one person should not reasonably affect what's happening to another person. Our number of trials is fixed, right? We're talking about 50 people in this ward. And so, right, our number of trials is fixed. And success chance is constant, right? We were talking about that with the independent trials. Obviously, we know, right? Not every single person has a fixed probability of dying from COVID, right? Some people are definitely at much higher risk. Some people are at much lower risk. But that is assuming we know some extra information about the patient, right? So for the sake of this problem, right, we know nothing about the individual patients. So all we can really go on is like the population average. So that's kind of what we're going to start with. So let's get back to the problem. So now we're asking ourselves, right, what's the probability? So we know that this is, we know that this is binomial. That we're good on. So now we have to kind of establish the formula for this. And the general formula, again, you can find this if you have a copy of the textbook, or if you can go onto Google Classroom and look at the scans of the textbook chapters that I put up there, then you're good. But so if we were to look at this, right, the probability, it comes down to this, right? So the probability of getting X successes, or sorry, let's do this. Okay, so let's say, what's our probability that the number of successes X is greater than or equal to, is equal to, we'll get to the greater than or equal to kind of situation after this, equals some value, let's call it K, is going to be equal to N and K, right? So N, this is the number of successes, and K, this is our failure, N is the number of trials. K is the number of successes. And trials, right? This was our, so this is like the number of different ways. So we might have to ask ourselves, right? Like how many, if we have 50 people, how many different combinations of 3 people could we have within that? And it's going to be a huge number. But so we can look at that, and then p, right, our chance of success, to the k power, right? So basically we're talking about k successes times 1 minus p to the n minus k, right? So again, p is the chance of success, 1 minus p is the chance of failure. K is the number of successes, n minus k is the number of failures. So this is the formula that we're going to use. Okay, so if we're saying what's the probability that 1 out of 50 will die? So basically we're saying what is the probability that x, the number of deaths, right? Let's make that clear, right? X is the number of deaths. And we're basically saying, all right, so what's the probability that x equals 1? And to do this, right, we're going to basically say, all right, out of a group of 50, how many different combinations of one person could there be? And of course, if we ask ourselves, right, how many different ways can we pick one person out of a group of 50? Well, there's 50 ways of doing that. Okay, so that's actually a pretty simple one. No calculator needed. And then, right, we're going to take our probability of success, right? It's weird to call death a success here, but basically satisfying our condition. So the probability of satisfying this condition is 0.5. And we're only looking for one example of this. So 0.5 to the 1 power, right? One death, or sorry, 0.05. Then times, well, if there's a 5% chance of death, there's a 95% chance of not dying, and we're assuming that now 49 people will not die. So this is going to give us, right, 0.05, right? Anything to the first power is just itself, and then we have 0.95 to the 49th power, which, here, let's see if we can bring up the calculator. Let me see if I can get that to work. This is all kind of a big experiment, so just bear with me, guys. So I'm going to bring up my TI Inspire software. Let me see if I can get that working on here. All right, I'm just getting this started up right now. Okay, there we go. Please let me know what's going on with the writing. You all should have seen all of that, but I have a feeling I kind of goofed on something. All right, so where's my TI? There we go. All right, so let's see if I can add this into the stream. All right, so we're gonna not do that, and then we are going to do calculator. There it is. Okay. All right, so hopefully we are seeing the calculator. Okay, so let's see what that looks like now. Let's resize this a little bit. Okay, cool. So hopefully you guys are seeing the calculator. Okay, so if we're doing the calculator business here, all right, so our problem was, okay, 0.95 to the 49th power. No, not working. oh, duh, need to actually add a calculator page. There we go, 0.95 to the 49th, and we get 0.080995. Okay, so let's switch that off. And that back on. All right, so hopefully we're good. So we said 0.08095. We multiply this out again. Let's do that here. And we get, so we have this times 50 times 0.05. So we have roughly about 20.2% chance of having one person out of these 50 die. Okay, so which, you know, is not great. You know, maybe it's a good thing that this is less than so right, approximately 20.2%. Okay. So how could we do this on the calculator a little bit more simply? Well, if we go to our favorite menu option, and then we go to statistics, distributions, and we pick out the binomial PDF. All right, our number of trials is 50, right? There's 50 people. Probability of success is, again, funny term to use here of success. And then our X value, we said, is 1. Enter, and bam, there we go. Perfect. 20.2487%. Okay, remember, anytime you're doing looking at one very specific value, that's the PDF, probability distribution function. So that's for X equals 1. All right, so now let's say, okay, let's keep looking at, let's turn off the calculator, turn the window capture back on. Okay, so what's the probability that 5 or more of these 20 will die? Okay, so we do want to look at the probability of 5 people dying, but we also need to look at something a little bit broader here. So let's try that out. So what's the probability that 5 or more of the 50 will die, right? So what does this come out to? Well, we're saying, all right, so what's the probability that X is greater than or equal to 5? Well, this is going to be, well, 5 people could die, or, and remember, when we do or with probability, we are looking at addition. Okay, plus P of X equals 6, or X equals 7, or on and on and on up to X equals 50, which, like, let's hope that never happens, that all 50 go, but, you know, that is a possibility in our situation. So, how do we do this, right? This is not one that we're going to want to do by hand, right? There's 45 different options. We could cut down on this by doing, right, saying that the idea that of having more than 5 deaths is the same as 1 minus the probability of less than 5 deaths, right? So that would cut it down, right? Instead of looking at 45 different options, now we would have 5 different options. But still, easier way to go is the calculator. So let's do it with the calculator. So let's turn off window capture. All right, there we go. So let's go back to this. So now, right, since we're looking at more than one specific value for x, we want to use binomial CDF. So again, we go to the menu, go to statistics, distributions, binomial CDF. Okay, so our number of trials is again 50. Probability of success is still the same, 0.05. So now our lower bound is 5, and our upper bound is 50. So these are inclusive boundaries. Okay, I'm like 99% certain that's true, but please let me know if I'm wrong. Okay, so if we did all this correctly, right, there's a 10% chance that 5 or more people will die. Which is not a great one, but it means there's, on the flip side, there is a 90% chance that fewer than 5 people die, which is something worthwhile. So we do have that, but that is essentially what it comes down to, right? So the idea here is we want to look at, okay, there we go, okay. So the idea here is we want to say, all right, let's give this some more room. All right, whatever. So basically what we want to do here is say, right, we are doing binomial CDF of 50, 0.05. Our lower bound was 5, upper bound was 50. And that came out to roughly about 10%. Okay. Let's make this a different color because, you know, what's the point of doing stuff on the computer if we can't take advantage of it being super colorful? Let's make this, let's make this a nice purple because I like purple. Okay. So, right, if we're looking at one particular value of x, that's PDF. Multiple possible values, that's CDF, cumulative distribution function. So how many deaths should we expect? So we'll wrap it up here. And for a binomial, the expectation, what we call the expectation of x, right, our variable, the number of deaths, is just going to be equal to, and right, this is the same as the mean value of that distribution. And so the mean value for a binomial distribution is n, the number of trials, times p, the probability of success. So in our case, that is 50, number of trials, times 0.05, the number or the probability of success. So multiply these out, we get an expectation of 2.5. So, right, you can't expect half a death, but you could say like, okay, so basically, you know, what would our expected be? We could say either 2 or 3, or we could, you know, just say 3 because it's more than 2. But either way, or you could just say, right, more than 2. So we should expect, right, 2 or 3 deaths out of the 50. Unfortunately, right, we would love to expect 0, but even with a 5% death rate, just not reasonable. Okay, so these are some examples of the binomial distribution. We're running a little long today, so actually I will save the second problem about geometric distributions for my next stream, which is hopefully tomorrow, April 15th. If it's not, I will keep you guys updated. Far as I can tell, I cannot really see the chat right now. It's saying unable to connect to chat. Hopefully there's maybe one or two of you here or not. I mean, hopefully we've got some viewers, maybe not. If you have any comments, feel free to leave them in Google Classroom. Go to the discussion page of my channel. However you want to get at me, get at me. So this is Miss A. Hope you guys have a very good day. Hope I did not bring you down too much with this problem, but hopefully you've also seen a little bit of how even just like some very, very, very basic statistics can still be really useful in this kind of an important situation. So that's it. Signing off. I will see you guys hopefully tomorrow.